In this video, we will introduce the Experiment Manager. The Experiment Manager assists you in executing simulation studies, which consist of several experiments that it automatically performs. Simulation studies allow you to investigate various variants of input values and achieve statistically reliable results. In a simulation study, we explore how model parameters, which are sets of input values, influence certain resulting values, known as output values. As you can see, we have set up a model with 3 stations, a source, a drain, and 2 buffers. Our aim now is to find the most optimal parameterization for the 2 buffers to get the most optimal throughput. To achieve this, we will insert the Experiment Manager from the class library. After inserting the Experiment Manager, we need to define output variables. You cannot start the Experiment Manager without doing so. There are 2 ways to define output variables. The first method is to drag and drop an object onto the Experiment Manager. This approach is particularly helpful if you do not remember the name of the attribute you want to use, as it provides a list of attributes from which you can choose. Here, we select stat numbering as we want to optimize the number of parts that enter the drain. We could also hold the Control key and select multiple output variables, but to keep the example simple, we will not do that. You can think of output variables as the target variables that you want to increase or, in some cases, decrease. After choosing the attribute, we can open the output variables and see that the attribute has been entered. At this point, we can optionally add a description for our reference. In the last column, we can determine if higher values are better for this attribute. Here we will obviously type true. You shouldn't leave the last column empty. In the report generated later, we will see the best parameterization of the variables. If you do not determine whether higher or lower values are better, Plant Simulation cannot know which result to show as the best result in the final report. The second way to enter variables is by doing it manually. You can press Enter and input additional variables as needed. After defining all the output variables, we now add input variables. These can be considered our dynamic variables, for which we will try different parameterizations to optimize the output variables. The first input variable we want to define is the buffer capacity. However, to enter input variables by drag and drop, we need to hold the Shift key while doing this. Then, we can select the capacity attribute of the buffer. We repeat this process for the second buffer. If we now look at the defined input variables, we will see that the 2 buffer capacities have been added. Similar to the output variables, we could enter these manually as well. After defining our variables, we can set up the experiments to be executed. To do this, click on Define Experiments in the Experiment Manager. In this table, you can define the input values. We call this type of parameterization static parameterization. In the first column, we can specify a name for the experiment. In the second column, we can define whether the experiment is active and should be executed in the simulation run. The columns following the second one are for specifying the values of the variables. We will try out capacities of 1, 10, and 20 for both buffers. After defining all the experiments, we can enter the number of observations for the experiments. Within an experiment, the Experiment Manager executes several simulation runs with unchanged input values and different stochastic behavior and determines the output values. For this reason, we call the simulation runs of an experiment observations. To carry out the observations and achieve different stochastic behavior in each observation, the Experiment Manager increases the random number variant of the event controller. To have a look at this parameter, open the event controller, click on Tools, and then select Random Number Variant. We have two parameters that affect the algorithm determining the random numbers. The first one is the random number variant, which is a global variable that serves as the initial parameter for the algorithm. The second parameter is within each object in the model frame. If we open the F8 dialog of any object and type random, we will see an attribute called random seed. So in each observation for an experiment, the event controller will increase the random number variant. By doing so, the random numbers will be changed, leading to different stochastic behavior in each observation. We can later reproduce model parameters by using the experiment number and the observation. In the text box labeled Observations per Experiment, you can enter the number of observations for each experiment. If there are no events depending on stochastic probabilities in your model, you would get the same behavior in each observation. As you know, stations tend to fail from time to time. So therefore, we have introduced failures at our stations by setting their availability to 90% and setting the mean time to repair to 4 minutes. Additionally, we have set the processing time to 1 minute and introduced a setup time of 15 and a recovery time of 10 seconds. Now, in each of the observations, different seed values are set for the station failures. This is precisely why each experiment is run multiple times with different observations to capture various failure times for the stations. The default number of observations is 5. If you are conducting the experiments to get a general sense of the outcomes, 5 observations is a good starting point. However, if you have more time or can run the experiments overnight, you might increase the number of observations to gain more detailed insights. In the result precision, we can determine the number of decimal places to show for the results. A value of -1 indicates that all decimal places should be shown. Now we switch to the Evaluation tab. Here, we can select different interval types to show later in the report. For the first run, we change the intervals from min and max to confidence. By doing so, we will get the confidence intervals later in the report. Lastly, we need to determine an end time for our simulation. To do so, open the Event Controller and switch to the Settings tab. Here, we define an end time of 10 hours. After doing so, our simulation is ready to run. To start the simulation, click on Start in the Experiment Manager. Once the simulations have run, we will see the runtime of the simulation and get a report. In the first section of the report, we will find an overview of the conducted experiments, including the mean value of the target variable. Each experiment was executed 5 times, and since the target variable's value may vary across these observations, the report presents the mean of these 5 observations. Upon further investigation, we can immediately see that we obtained an increase of around 49 parts when comparing a buffer capacity of 1 to 10. However, we only achieved slightly better results for a capacity of 20 compared to 10. There is only a change of 4 parts when we double the buffer capacity. In the next 2 sections, we can review the input and output values. Then we will see the statistical evaluation. Here we can see the confidence intervals, detailed results, and the p-values of the t-test. The confidence interval is a range of values believed to contain the true number of parts that end up in the drain. This range is calculated from sample data and is associated with a confidence level, typically expressed as a percentage. In our case, we use a confidence level of 95%. The confidence level indicates the degree of certainty that the number of parts lies within the interval. For instance, if you calculate a 95% confidence interval for the number of parts ending up from an experiment, it means that there is a 95% probability that the results of simulation runs with different random seeds will be in this interval. Confidence intervals offer insight into the precision of your estimates. The left interval bound is 444, as we can see from the detailed results, whereas the right interval bound is 482. The line within the box marks the median value. A narrower interval signifies more precise estimates, whereas a wider interval indicates less precision, thereby quantifying the uncertainty around the estimates. By providing a range, confidence intervals reveal the variability and reliability of the results concerning the number of parts in the drain. To assess the stability of your model's predictions with confidence, the standard deviation can be examined. A high standard deviation suggests significant variability and less stability in the model's predictions, indicating that the target values deviate considerably from the mean. Conversely, a low standard deviation suggests that values are closer to the mean, indicating more consistent and stable results. Then we can see the p-values of the t-test. P-values help us determine the statistical significance of the differences between the means of our experiments. They indicate the probability that the observed differences occurred by chance under the null hypothesis, which assumes no real difference between the groups. Let's have a look at the first row. The p-value of 0.001 suggests that there is only a 0.1% chance that the difference between the means of experiment 1 and experiment 2 is due to random variation. Since this value is less than 0.05, we consider the difference statistically significant, meaning the increase in the number of parts from experiment 1 to experiment 2 is likely due to a real effect rather than chance. The remaining value in this row is even lower than the first one, so the same conclusion applies. If we now have a look at the p-value of experiment 2 and 3, we have a higher p-value. A p-value of 63% suggests no significant difference between the means of experiment 2 and experiment 3. This high value indicates that any observed difference is likely due to random variation, so we cannot conclude a real effect between these experiments. In practical terms, this means that changing the buffer capacity from 10 to 20 did not have a significant impact on the target variable. The observed increase of around 4 parts is not statistically significant and is likely due to random fluctuations in the simulation results. By examining the p-values, we determine that the significant increases in the number of parts occur between experiment 1 and the experiment 2. However, there are no significant differences among experiment 2 and experiment 3. This analysis helps us understand where meaningful changes happen and where they do not, guiding us in making informed decisions based on the simulation results. Currently, the confidence level is set to 95%, but we can change this in the settings. To do so, open the dialog of the Experiment Manager, click on Tools, and then click on Advanced Settings. Here, we can change the confidence interval if desired. We can also change the interval types back to min and max. Then we reset the model and start it again. If we now examine the statistical evaluation, we will see min and max intervals. Now, the left bound of the plot shows us the minimum value of the observations, which is 449, as we can see from the detailed results, whereas the right bound shows us the maximum value of the observations, which is 488. The left bound of the box plot shows us the lower quartile, Q1, and the right bound shows us the upper quartile, Q3. This means that 50% of the observations lie in this box, also referred to as the interquartile range, IQR. You can adjust the visualization of the intervals according to your needs. In the last section, we can see the best parameterization. Obviously, here we see that a capacity of 20 gets the best result, however, with just an increase of around 4 parts compared to a capacity of 10. If you are primarily interested in achieving the highest throughput, you can set the capacity to 20. However, we should investigate the range of capacities between 1 and 20 in more detail, as there appears to be saturation beyond a certain point. So we should look for more precise increments, and need to evaluate all possible permutations up to a capacity of 20. So let's return to the Experiment Manager and open the experiments. Entering all possible permutations into this table manually would be very time-consuming. Fortunately, we have tools available to assist us. Let's close the experiments and click on the Tools tab in the Experiment Manager. Next, click on Multi-Level Experiment Design. Here we can define the upper and lower bounds, as well as the increment. Then the tool generates all possible experiments for these parameters. Let's set an upper level of 20 and keep the lower level and increment at 1. Clicking OK now will generate 400 experiments. The previously defined experiments will be overwritten, so let's proceed by clicking Yes. In the upcoming dialog, we will see all permutations of the experiments that will be executed. Click OK again to confirm and start the simulation. The execution will take some time because for each set of experimental conditions, we will run 5 simulations. Once the experiments are finished, we will again see the duration of the experiment run and access the HTML report that offers insights into the experiments. Now we switch to the last section of the report. As we can see, we get the same amount of parts in the drain for all these experiments. Obviously, the most optimal one for us is the one with the lowest buffer capacities. By using the Experiment Manager, we found that we can reduce the capacity of the buffers by 7 and still achieve the same result as if the capacity was set to 20. These are great results, considering that larger buffers may require more space and incur higher costs. However, at this point we should still consider that we only increased the throughput by 4 parts compared to a capacity of 10 for both buffers. So, you need to decide whether you want to further investigate the results or if you are satisfied with these buffer capacities. Now let's reopen the Multi-Level Experimental Design dialog again. We can see that we have generated 400 experiments with just 2 variables. Adding additional variables would increase the number exponentially. Typically, these experiments would run overnight. However, there is another method available. It's the second option under the Tools tab. The Random Experiment Design randomly selects values from a defined grid. This results in fewer experiments that can be executed quickly. If you are interested in recreating the model parameters for a specific experiment and observation, you can do that easily as well. To do this, click on Tools, then on Advanced Settings, and switch to the Validation tab. In the Model Parameterization section, you can enter the experiment and observation number, and you will get the parameters for these settings. In the last section of the Experiment Manager, we can let the simulation run distributed. This allows us to use the additional cores of our computer. To showcase this, we can click on Tools, then Advanced Settings, and finally on Distribution. Here, we can activate the distributed simulation. If we do so, we will see our computer referred to as localhost. If we double-click on it, we can specify how many cores we want to use. For each core, a planned simulation application instance will be started, with each instance executing 1 observation. However, it is important to note that using distributed simulations is not always advisable. For short experiments, the overhead of starting multiple application instances and running the simulation may result in longer overall execution times compared to running it in a non-distributed manner. Additionally, performance does not scale linearly with the number of cores. Using 12 additional cores will not necessarily yield results that are 12 times faster. This is because all cores access the main memory, as the CPU cache of each application is not sufficient to handle all operations independently. The bottleneck here is usually the data bus, which is responsible for transferring data between the memory and other components. When one core writes to the main memory, other cores may need to wait, thereby limiting the performance gains. For this reason, it is usually not beneficial to use more than 4 to 5 cores on desktop computers. However, keep in mind that this is highly dependent on your model and your computer. Let's imagine that one experiment would take 1 minute to execute, and we want to conduct 50 observations for this experiment. That means each experiment would take 50 minutes to execute. In such cases, distributed simulations can drastically reduce this time. However, in our current model, it would not bring any benefit to run the simulation distributed, as it is too simple. So let's first set the end time of our simulation to 1000 days. Then let's deactivate distributed simulations and start the simulation. You will now see that the experiments are executed very slowly, as the end time of the simulation is at 1000 days. In such scenarios, it is now advisable to run the simulation distributed. So let's reset the run. Now we activate distributed simulations. When we start the simulation, we will be asked if we want to save our model. Please keep in mind that we need to do this, as we have changed the end time of the event controller in the model and not saved the changes yet. If we do not save our model before executing the distributed run, the remote processes would use the last saved state of our model, where we had not specified an end time, which would then lead to an immediate termination of the remote processes. Therefore, it is advisable to save your model after making any changes before running its distributed simulation. If we now start the simulation, you will notice that first we need to start the remote processes, which also takes some time. To gain more detailed insight into the ongoing processes, we can now additionally open the progress table. Here, we can see which experiment is currently being executed. As we have selected 12 cores, the experiments are executed in batches of 12. Another crucial consideration is the capacity of our main memory. In a distributed simulation, multiple plant simulation application instances run concurrently, and each one allocates space in the main memory. Thus, it's essential to consider memory capacity when determining the number of cores to use. Given that our current model is a simple example for this video, let's examine a more realistic scenario. Therefore, we will open the Factory 51 model. To see how much memory a model will use, we can fast forward the model for a bit and then stop the simulation. Then we can click on File, Help, and then on About Plant Simulation. In the upcoming dialog, we will see the peak memory allocation. For our model, it shows around 643 MB. Next, we need to determine the total available memory on our system. To do this, we open the Task Manager. Here, we can see the total and available memory. However, it's important not to allocate all the free memory to plant simulation instances. Ensure you leave at least 1 GB of free memory for other applications to avoid system performance issues. With this, we have concluded the introduction to the Experiment Manager.